So today we're going to look at circuits that contain both a capacitor and a resistor, or an inductor and a resistor. And while there's some good calculus behind where these equations come from, it can be very handy just to use these equations when you're looking at these kinds of problems, because these will help you get to the answer that you need to get to. So the first one here is gives you the voltage across a capacitor as a function of time. And so this is a function. It's in terms of t. It's not a number. It gives you a function that you can look at it and say, okay, well, at this time, that's what the voltage will be. And this is given assuming that you're starting at time t equals 0. And so if you're starting at time t equals 0, what you need to find to use this equation is what the voltage is at infinity and what the voltage is at 0, and you need to find the time constant. And the time constant for an RC circuit, and this is for an RC circuit, it's got a resistor and a capacitor, the time constant is R and C. And you want to look at your circuit during the time period that you're describing to determine what the resistance is. Now, like I said, this is assuming you're starting at time t equals 0. Well, let's say you're not starting at time t equals 0, and you're starting at time t equals t naught. Then instead of this equation, you would have Vc of t equals Vc at infinity. And by infinity, we mean what would it look like at infinity if it stayed the way it is, if the circuit stayed the way it is right now. You might know that something's going to change in the future, that a switch is going to be turned, or a function's going to change. But by infinity, we mean what would it be at infinity if it was like it was right now, plus Vc at t naught, where that's the time that you're actually starting, minus Vc at infinity. E, now I write it, rather than saying minus t over tau, I write it as minus 1 over tau. So rather than finding tau, I find 1 over tau. It just makes for a prettier looking answer at the end. So minus 1 over tau times, and this would be t minus t naught, because we didn't start at 0, we started at t naught. So that would be if you started at time t naught. And then the current through a capacitor is given by C dV dt. So if you need to find the current instead of the voltage, then you find the voltage, and then you take the derivative and multiply by C to get the current. Now, for an inductor, we have a very similar equation. So our inductor looks a lot like the one for a capacitor, but instead of voltage, we have current. And I would also write it like, so IL at infinity plus IL at 0, or whatever time you're starting at, minus IL at infinity, and then e to the minus 1 over tau times t. And tau for an RL circuit is L over R. So for each of these things, what you have to do is you have to find 3 things. So for the RC circuit, you have to find Vc at 0, you have to find Vc at infinity, and you have to find tau. And if you have those 3 things, then you can come up with your equation. For an RL circuit, you also have to find 3 things. You have to find IL at 0, IL at infinity, and tau. And tau for an RC circuit is RC, and for an RL circuit is L over R. And the R is the equivalent resistance of the circuit. It's the Thevenin equivalent resistance. And so what you do to find that is you short out voltage sources and you make open current sources, and then you look and see what the equivalent resistance is from the point of view of the capacitor if you're doing an RC, or from the point of view of the inductor if you're doing RL. So I'm going to save this real quick and then see if y'all have, I'll ask first if y'all have questions. So are there questions? Yes?
For the equation on the top right, we put like e to the negative 1 over tau.
Uh-huh.
Why should we put 1 and then multiply it?
Okay, because this equation is minus t over tau, right? Isn't that the same as minus 1 over tau times t? This is t minus t naught, because this is if we're starting at t naught. So this is like if we're starting at time 2 seconds rather than at 0, then up here we would have t minus 2. That's where that's coming from. So this is a different formula, and that's why I have VC of t naught here instead of VC at 0. We're going to see one of those in the problems for today where it's actually piecewise. We start at 0 and then we do something and then we change and we do something else. Okay. Other questions?